So I'm presenting on the paper recognizing the goals of uninspectable agents, which we worked on with some colleagues at Northwestern and NRL, although about half of us have moved on to the next place at this point. This work is at the intersection of theory of mind reasoning, which is which Adam just explained for us very well, but it's from a concept out of psychology, which describes the process of inferring the internal states of others. It is something that we as people do all the time in all of our communication and interactions. Thinking about our beliefs, desires, intentions, knowledge states, and goals. Goal recognition is a concept that's probably familiar to many of you because it is a concept that comes out of this community. And that's the process of inferring the goal of an agent from a sequence of observations. And observations in this case are things like actions, states, and action state pairs. There's a lot of prior work on this that I won't have time to go into, but it's been used in a lot of domains, and there have been many, many different types of approaches to goal recognition. The main difference between theory of mind as it's defined in psychology and goal recognition as it's defined by this community is the kind of information that is reasoned from. So from theory of mind, you use what we are calling external information. So the sort of information that you can observe, right? I can see someone walking in the general direction of the kitchen, but I don't necessarily know that they're actually going to the kitchen or that they're going to the kitchen to the kitchen sink, right? Goal recognition uses observations that sometimes contain information about what we are calling internal states of an observed agent, right? So I'm going to the kitchen in order to talk to a specific person, right? There's a target of the action that's often included in the observation. So what we want to do in this work is take a look at two problems. First, whether a computational approach to theory of mind can do goal recognition at a level that's similar to specifically goal recognition approaches. And we want to see how different levels of available knowledge affect how well each approach performs. So two main contributions of this work then are first demonstrating that the analogical theory of mind model can perform goal recognition, and then comparing that model's performance to a state-of-the-art goal recognition system under three knowledge conditions. So full internal information, which is information coming out of the agent's planner. What we're calling partial internal information, which is information that's coming from the agent's execution trace, so it's actual execution in an environment, what it actually does. And then no internal information, which is an anonymized version of that execution trace. And I'll show you examples of all of these in a little bit. The analogical theory of mind model is a computational model, computational cognitive model, I should say, of human theory of mind reasoning and development. We've validated it on several studies from psychology, showing that it learns in the same ways as children do. It uses the analogy stack from companions under the hood. So for the purposes of this talk, we're looking at training observations that are then from which we build up models that uses the structure mapping engine and the sequential analogical generalization engine to build up those models. So briefly, what SME does is given a structured representation, and here we're going to use a farming example because that's the task we'll be talking about in a little bit. So here you have an agent that plants a pumpkin, and that causes the pumpkin to grow. Compared to another case in which an agent plants a carrot, and that causes the carrot to grow. So what SME does is it finds matching predicates and makes correspondences between them. And then based on those correspondences, it makes correspondences between the entities that are involved in the two cases. These are combined into a match score, and that score tells us how similar the two cases are. So the match score between these two would be pretty high. The sequential analogical generalization engine takes that mapping, and assuming that the score is high enough, it forms a generalization between the two cases. You can think of the generalization as a schema. So what that looks like here is that an agent plants something, 50% of the time it's a pumpkin, 50% of the time it's a carrot, and that causes that something to grow. So we build up those models during training and get a case library of models in that way, or generalizations. So when we then have a test observation case library, we, during testing, retrieve using MaxVac. MaxVac is a two-stage process for retrieval. In the first stage, it's just a content vector dot product for quick retrieval. And then the second stage is that same alignment using SME that we talked about a couple slides ago. So you get the best retrieved case, and from that you get a label, and that label is going to be what we use as the goal. The the planning approach that we use for goal recognition is the planning and acting in a network decomposition architecture, or PANDA. This is an off-the-shelf model that we use as it's given. And what PANDA does is it converts an HTN planning model into a new model specifically for goal recognition. So it takes a set of actions, it takes a new planning model, and it gives you the goal that it thinks you're doing. Because we needed those several different levels of information to be available to us, we created our own data set in Minecraft. We chose Minecraft because it's a open world sandbox game. It was open sourced by Microsoft specifically for AI research a few years ago, so it's pretty easy to hook into. But it also opens up for a large variety of tasks for us to be able to work with in the future, and also gives us some built-in systems that we can take advantage of now in order to test our goal recognition work, our systems. The actual recognition task is trying to figure out what an agent that's doing a farming task is actually trying to do. That agent has the goal of maximizing its food points, which is based on Minecraft's internal food point system. And our agent is trying to, either the theory of mind agent or PANDA, is trying to recognize which specific farming task is taking place. So there are lots of possible tasks. Most of them are hierarchical. So for example, if the agent is making bread, it first has to find some wheat seeds, and it has to grow the wheat, and then it has to fertilize it, pick it, etc. And in order to make this a little bit more complicated than assuming that the agent is always just going to go for the highest points available, the agent also has a preference to be an herbivore, omnivore, or carnivore. So an herbivore agent is never going to hunt a chicken. A carnivore is never going to grow carrots. That sort of thing. That is hidden from the recognition model. So the agent is the Minecraft agent is a SHOP2 agent, entirely plan-based. Plan is parsed, converted into an executable sequence of actions, which is executed in the Minecraft environment. And these are where we actually get our data from. So here you see a list of the top level goals that are available to the agent. I think this is actually a partial list. But you can also see the sub goals that make this very hierarchical, right? Sometimes you have to make an intermediate product. Almost all of the time you have to gather some additional ingredients. You have to grow some crops, use some items that might be in your inventory. And then you have the actions that actually complete the task. So movement, looking, selecting items, the actual act of crafting. Right? All of these are the low-level actions that we're actually looking at. So to generate the data set, we made 10 pseudo-randomly generated maps with items randomly dispersed throughout those. And we had the agent play on each map for 180 seconds. We found that 180 seconds is plenty of time for the agent to complete several full plans. Depending on the plan, on the map, and the available resources, how many plans it completes during that time varies, which is why we then had to had to subsample from that set. But we had 5 sessions on each map. You can do the math to approximate how many traces we actually ended up with. So when we then subsampled, we had 100 random plan traces that come directly from the SHOP2 output. That's going to be our full knowledge condition. 100 random action execution traces, not random action execution. But so those are the actions that are actually happening in Minecraft. And that's going to be our partial knowledge condition. And then anonymized versions of those actions, which are going to be our external knowledge condition. So what those look like here is, so in the full knowledge condition, you literally have the plan as it is sent to the agent. In the partial knowledge condition, you have what the agent actually does. So now instead of looking at the crop on the farmland, it's just looking at the farmland. And in the external knowledge condition, now you're looking at some object. So every entity was anonymized to just be an object, because we know that someone is looking at something. We know what someone is physically doing, but we don't know what specifically they might be looking at or what they might specifically be moving to. We're thinking at us here being us as people, or an agent in an environment where it doesn't have access to the planner of any other agents. So to run the actual experiments, Panda was given 3 types of HTN models, 1 per condition. So in the full knowledge condition, it was given an adapted version of the SHOP2 model used by the Minecraft agent. In the partial knowledge condition, it was given an HTN model of the action executions, so using the predicates that are available at that stage. And then in the external knowledge condition, it was given an adapted version of that HTN model, now trying to rely less on the actual entities and the types of those entities. Atom was trained and tested using tenfold cross-validation because it needs to learn the models. So we took a subset for training and then tested on the other examples, and then the next fold, take the next subset, et cetera. And just to keep ourselves honest, we also had 2 random baselines, one that's purely random and the other one that always just picks the goal that is most common within the data set. And what we found is that Panda, as you might expect, performs extremely well in that full knowledge condition. So when it has full knowledge, when it has access to the agent planner, it performs at 100% accuracy, which is pretty impressive. Atom in that condition performs at 92% accuracy, so not too bad, but that is significantly worse. And as you can see, the random baselines are well below either of those numbers statistically as well. In the partial knowledge condition, Panda drops down. Now it's at 63% accuracy, right? So this is where it's getting just execution traces. It's also at 63% accuracy in the purely external, so when it's anonymized data coming in. Whereas Atom stays at 90%, or right around 90% in both of those conditions. So Atom is a little bit more robust, or significantly more robust, I should say, to changes in available knowledge. We also ran a quick experiment to see whether they can transfer information between the 2 conditions. So suppose you're in an environment where during training you do have access to the other agent's information, but you don't have that access to that information anymore during testing. How well do you do there? And Panda drops way down to 30% accuracy, whereas Atom is still right around 90%. So what we've seen here overall is that Panda is at 100% accuracy when it has full planner information available to it, but it decreases quite a bit when it has only actions or only external information available, to when it doesn't have access to the actual planner. And it does even worse, performs even worse when it doesn't have access to, when it has to transfer between knowledge conditions. Atom, on the other hand, maintains about 90% accuracy as that availability of information changes, which is an interesting finding and maybe suggests that looking at cognitive models to perform some of these tasks may be in some ways better when we're trying to expand the use cases. So there are a few directions of where we'd like to go with this for future work. course, we'd like to expand on what we've done here and to see whether we can do it in real time, and also to see whether the agent, whether we can use that information, use our inferences in order to give, in order to help an agent, help the agent that's actually in the Minecraft game. So switching to an online goal recognition experiment, connecting them into the Minecraft environment, and then seeing if we can actually send messages to the agent inside the Minecraft game to help it perform better. We'd also like to test with other goal recognition approaches. Like I alluded to earlier, there's lots and lots and lots of them with various different approaches to goal recognition and plan recognition. And we'd like to see whether any of them are robust to external knowledge, right? Whether they can perform goal recognition. Panda seems to not do quite as well when it has less knowledge available to it, but maybe there is a more classic goal recognition algorithm out there that can do that. So we'd like to take a look at that. And finally, and this one might be the next step, some of you may have picked up on the fact that Atom learns a model in order to do goal recognition. Panda is given a model, and we can talk all day about the trade-offs between learning versus being given one, given a model right there. And there are definitely many of those. But we're curious to see whether the model that's learned by Atom can be used by Panda, and whether the model that's given to Panda can just be used by Atom to avoid, and what the trade-offs are there for each of the two models. I talked a little fast, so we're at the end of the talk at this point. Hopefully there are some questions that I can clear things up about. Huge thank you to all of my collaborators, and of course to all of you for listening. So thank you very much.
All right, thank you, Irina. So from the Slack chat, we have, first of all, a question from Matt Clank. Given that the goals are continuous, i.e. maximize production, all plans would be of infinite length. Are the tasks limited to a set number of actions?
So we consider a plan to be done once the agent has whatever food it is going for. So if it's making pumpkin pie, it has pumpkin pie in its inventory. That plan is done. So that's how we're limiting the length of the plans. And of course, we don't include the actual making of the pumpkin pie and the traces that we're working from.
All right. Shiwali asks, are you considering further research on how to acquire knowledge necessary for modeling other agents? Does SME and/or SAGE support this research, and how might it be done?
Oh, that's a great question. So right now we're working from the OpenPsych knowledge, or sorry, not OpenPsych, the NextKB knowledge base, which includes OpenPsych and a few other open source knowledge bases as well in there. Gathering that information is the type of knowledge that you need is a very interesting question. I do think that it's something worth looking into because right now there is a lot of kind of going in and figuring out which parts of the knowledge base do we need to use and what's missing from there, what can we add to it. Of course, all of this is reusable, so it's not the worst thing in the world, but doing it in an actual experimental way where we're learning the knowledge would be good. I haven't thought about more specific approaches to how to do that. I know there's some work into learning by reading, for example, that I think Danilo Ribeiro in Ken's lab is working on that might lead in that direction, but I haven't thought about it myself that much.
Okay, Tom Henricks asks, what counts as a goal here? He points out that HTNs don't have goals, they have tasks. So is it inferring higher level tasks from observed subtasks?
Yeah, so it's yes, it's a higher level task. So if in order to make pumpkin pie, you need to grow pumpkins and you need to get some milk and you need to get sugar cane and whatever else, right? It's all of those subtasks. That's what we're seeing is the movement to get them, actually picking them, all of those steps. And then the final step is making pumpkin pie, and that's what we're calling a goal. So those are set a priori. We know ahead of time what the options are, and those are what the higher level plans are working towards accomplishing.
Sampath Gojaneni asks, how does an agent choose a structure when there are multiple potential ones to recognize goals?
So here here we literally just use the trace as it's coming out. So the one coming out of the planner is exactly the one that's being sent. It's the one that's being sent to the agent with some slight modifications in order for Panda to be able to process it. And the same for the other two. So in this case, actually the structure is remarkably flat. And we can talk about that maybe a little bit later about why Adam still seems to do as well as it does despite that.
So Justin Lee wants to know about Adam's failure cases in the perfect information case.
Let's see. Failure cases in the perfect information case.
I believe
I'm not sure I'm interpreting that right.
I believe your results showed that Adam did not have perfect performance.
Oh, I see.
Given perfect information.
Okay, in the full knowledge condition, yes. So that's a good question. So the mistakes there are actually kind of telling. For the most part, when it makes a mistake, for example, if it's saying the kinds of mistakes it makes are for growing, it thinks it's growing carrots when it's really growing potatoes, or it thinks it's hunting a chicken when it's really hunting a cow. So those are the sorts of mistakes that we're seeing, and that actually goes back to that previous question about the structure. I think because the structure is flat, we're seeing very similar predicates between the various growing tasks and the various hunting tasks, and the various putting the bigger cooking tasks like making pumpkin pie or cake or what have you. So those are where it makes mistakes.
Okay. Clifton McFade is next. He asks whether in the action-only conditions, the temporal representation is a strict sequence of primitive actions, or is there a hierarchy in terms of the actions? Especially if it's a straight sequence, how robust would this be to imperfect action sequences? He gives the example of an agent looking at a cow instead of farmland.
Yeah, so that one is so that is coming just straight out of the execution sequence in Minecraft. It's exactly what the agent, the actions that the agent is performing. And I think that may be why Panda suffers a little bit in that case, because, you know, like the question says, sometimes you're looking at the cow and sometimes you're looking at the farmland that it stands on. I think that's where Panda's mistakes may be coming from, whereas Adam doesn't quite care so much because of the models it's built up.
Okay, great. Well, thank you very much, Irina.